Okay, so this lesson is about two things. First, it's about recentering and rescaling data and how that affects summary statistics. Then I'll talk briefly about percentiles near the end. Percentiles have another fancy name, but we'll wait on that. First, I want to talk about recentering and rescaling data. So over here, I've made up some vehicle speeds and put them into a plot. So these are in miles per hour down here on some stretch of freeway or highway or something like that. And I've collected some amount of data. I don't know how much data is here, but some amount of data points. Looks like the slowest vehicle was going around 41 miles per hour, and the fastest vehicle was going around 66 miles per hour. So I want to display, and I also want to compute the mean. So there's a display of the mean. Oh, and it tells us right down there. That's useful. There's the display. Let me move these up here. I can extend this downward. So the mean speed is 55.02 miles per hour, about 55.03 miles per hour. And I also want to see the standard deviation. Now, plotting the standard deviation by itself doesn't do any good because it'll be some low number off the track. So what I'm going to do is I'm going to plot the mean plus the standard deviation. And so the mean plus the standard deviation is around 60. So you can see the width of this strip here would be the standard deviation. And I can display them over here in a summary table. So let's put the mean here. There's the speed. It automatically does the mean. And let's add the standard deviation. So there we have the mean and the standard deviation of this data. The mean speed is 55, right around 55. Standard deviation is about 5.22, and that's how wide this band is. It's around 5.22, so that's the standard deviation of the data. So recentering the data simply means adding or subtracting a value from all of the data points. So for example, I could wave my magic wand and make all these cars go faster. I can simply drag these points over and speed up all the cars. There we go. I've added around 5 miles an hour to all their speed. When I do that, how does that affect the mean and standard deviation? Well, it's pretty intuitive that if you speed up everything by 5 miles an hour, the mean speed is also going to go up by the same amount, and that's exactly what we see here. Okay, if I undo that, I can see there I was at 55, and then if I slide it over now, so I guess I went up by 4 miles per hour. And so when you recenter, when you add or subtract a constant from all the data points, the mean is affected in the same fashion. I've added 4 miles an hour to all the vehicle speed, and I've added 4 miles an hour to the mean. However, because we haven't changed how the data is spread out, I've just shifted them over. They're shifting to the side, but they're spread out the exact same amount. Since the standard deviation is based on variances, differences from the mean, the standard deviation is completely unaffected by rescaling. And that's these two represent a general trend for what happens when you recenter some data. So when you're recentering data, to type here so you can see all my typos. Recentering data means adding or subtracting a constant from all the values in the data set. Measures of center, like mean and median, have the same value added or subtracted. But measures of spread, like standard deviation or range or IQR, are unaffected. They maintain the same exact value after you recenter. There's no change in them whatsoever. So that's basically the story on recentering. Measures of center have the same value added or subtracted that you added or subtracted to all the points in the data set, and measures of spread are completely unaffected. When you recenter, you've not changed how the data is spread out at all. So the standard deviation, IQR, would remain the same. Rescaling, instead of adding a value to all these, we would multiply them by something. So for example, let's say I wanted to convert these speeds to feet per second. So let me bring up the raw data. I'm going to make another column here. So here's the data. And I'm going to make a new column, which is going to be speed feet per second. And I happen to know that the conversion factor is 88 feet per second is the same as 60 miles an hour. So if I multiply these by 88 and divide by 60, I will get a conversion to feet per second. So here's feet per second now. So what will happen if I plot speed in feet per second instead of speed? What will happen to the mean and standard deviation? Can I copy this? No, I can't copy this. I have to make a new graph or write over it. Let's make a new display. So let's make a new graph, and we'll put speed in feet per second on this one. So notice right away that I can put this aside. I don't need this sitting open anymore. There we go. Get this out of the way. Notice immediately the shape is the same. By rescaling, by changing the units down here, I haven't changed the shape. Okay. What have I done to the mean and what have I done to the standard deviation? Well, the mean is going to be in the same place in the data. It's going to be right on top of this line, but that's over a different number now because we've rescaled down here. So if I plot the mean, so I find that the mean, let me bring it up here so I can see it. There we go. I'd like these to be stacked so I can see them one by one another. There we go. So the mean now is 80.7. And of course, what that is, that's the same rescaling factor applied to the mean. If I were to take this mean here, multiply it by 88 over 60, my rescaling factor, I would get 80.71 feet per second. And in the same fashion, the standard deviation, as opposed to before, when you recentered, the standard deviation was unaffected. The standard deviation will be changed. Mean plus standard deviation. So now the standard deviation, it looks the same as this, but notice the scales are different. I've rescaled this axis, and this difference now is in the range of about 7 point something. It's larger, and it's larger exactly by the rescaling factor. I multiplied everything by 88 over 60, so the standard deviation will be multiplied by 88 over 60. If I replace this speed here with speed in feet per second, you'll see both the mean and standard deviation have been multiplied by that rescaling factor of 88 over 60. There's the original, and there they are multiplied by 88 over 60. So let me summarize this over here. I'm just going to copy and paste to be lazy and then change what needs to be changed. So rescaling the data means multiplying by a constant. Multiplying a constant by all the values in the data set. Measures of center have the same value multiplied. As do measures of spread. So summarizing, if you add a constant to other values in the data set or subtract, you'll affect the center but not the spread. Measures of center will be increased or decreased, measures of spread unchanged. If you multiply by a constant, both measures of center and measures of spread get that multiplication. Or another way of looking at it, measures of center respond to both addition and multiplication. Measures of spread only respond to multiplication. Adding has no effect on them. Yeah, there's one more topic for this lesson. It's a pretty short lesson. You'll have time to work. The other thing I want to talk about is percentile, or the fancy name for percentile. Cumulative, relative, frequency. Very fancy name. What I've created here, let me bring this up here. I did this earlier. This is going to be a scary looking plot, but you don't need to be able to make any of these. You're familiar with this idea of percentile. You've seen this before. What percentile measures, and cumulative relative frequency is just another name for percentile, measures the percentage of the data that is at or below, that is, well, let me rephrase that, that is equal to or below or less than a given value. Percentile can be a little bit confusing if there's several values in the data set, like in the one that we're seeing, that are equal. So this percentile plot here shows the same data as over here, but it's a different view. Going along here, we still have the speed, but now on the vertical axis, instead of just a frequency, we're plotting the percentile, the percentage that are equal to or less than the given value. And you can see they stack up here when we have a lot of equal values. Like here's these ones, that big stack that were at 51 miles per hour. So they're stacked up here. Generally, by this definition, what we would take for the percentile of all those, since we're taking a percentage of that as equal to or less than, is we would take the highest value from this group right here as the percentile, right up there at the very top. So 51 miles an hour, we would say, is, if I look across over to here, is around at the 28th percentile. So that means 28% of the data is equal to or less than 51%. So when I look over here, 28% of the data is right there. That's 51 is at the 28th percentile. And if I look over here at, say, maybe that, what is that, 63 miles per hour, and trace this across, take the highest value there, that looks to be maybe 95%. So I would say, oh yeah, I can see it over here, that's 67 miles per hour. So I would say 67 miles per hour is at the 95th percentile. So this would be 95% of the data, and only 5% is higher than that value. It's used very frequently to enable comparison, to say, you know, you've seen this when you get SAT scores reported or things like that. You say so-and-so is at a certain percentile, so you see, okay, I got, you know, a 690 on an SAT, and what is that good? And you learn that, oh, 690 is at the 80th percentile. I don't know, I'm just making stuff up. So that means 690 is 80% of the data is equal to or less than 690. So that means you did as well as 80% of the people took the test and 20% of the people did better than you. So that's one way of interpreting what percentile means. The reason it's called cumulative relative frequency, frequency just means count. Relative frequency means proportion. So it would mean what fraction are at a particular value. So if I wanted to know what percentage of the data is equal to 51% right there, that would be the relative frequency as opposed to the frequency. Frequency would just be how many, you just count the dots. It looks like there's 11, what have we got, 3, 3, 3, it looks like 13 dots there. So 13 out of 13 dots would be the frequency. 13 divided by the total would be the relative frequency. And then cumulative always means up to and including that value. So that's why we end up with cumulative relative frequency being another term for percentile. One last note, Q1, the first quartile, is also at the 25th percentile. Q3, the third quartile, is at the 75th percentile, and hopefully, obviously, Q2, the median, is at the 50th percentile. And that's that.